Hi, ladies, Mr. Sullivan. Today we're going to be looking at lesson 7-4, geometric sequences. So the past few days we've been studying arithmetic sequences. What we're going to be doing today is we're going to be studying the geometric sequence. So the way geometric sequences work, we'll be exploring shortly. Today's learning target is I can apply the definition of a geometric sequence by finding a specified term and constructing the nth term. So geometric sequences are a sequence of numbers where each term after the first is found by multiplying the previous one by a fixed non-zero number, called the common ratio. So the common ratio is sort of like our common difference, but we find it by multiplying. So whenever we're multiplying, is that a linear function or an exponential function? Geometric sequences are examples of exponential functions for that very reason. So when we're multiplying, we have exponential functions. So what we're doing is we're actually just writing an exponential function for a sequence. So the general form of a geometric sequence is provided on your reference sheet. And this one we're not going to modify like we did with the arithmetic one. We're going to leave as is. It is a sub n equals a sub 1, or your first term, times r to the n minus 1. So a sub 1 is again your first term, and the r is your common ratio. What you multiply by. So if we look at these two examples, we're given two sequences and we want to find the next two terms. We want to figure out, is it geometric, what the common ratio is, and our formula. So if we look at the first sequence, we have 2, 6, 18. So if I look, when I go from a 2 to a 6, I multiply by 3. When I go from 6 to 18, I multiply by 3. So I'm going to keep on multiplying by 3. What's 18 times 3? Very good, 54. Then I multiply by 3 again. What's 54 times 3? It's 162. So those are the terms of my sequence. And remember, it goes on forever, ever, and ever. So if I look, this is geometric because I'm multiplying by a 3 each time. My common ratio is the number I'm multiplying by. What number am I multiplying by? Very good, a 3. So I can say r is equal to 3. And now what we do is we rewrite our formula. So I'm going to go up here and actually copy and paste this. My a sub n equals a sub 1 times r to the n minus 1. And what we're going to do is we're going to make some substitutions. We're going to rewrite our a sub n. We're going to write our a sub 1, and in this case, our a sub 1 is going to be a 2. And now we're going to have the number we're multiplying by, or a common ratio, which in this case is a 3. And this is my final answer. A sub n equals 2 times 3 to the n minus 1. All right, let's go on to our next example. In our next example, we have 4, negative 20, 100. The first thing we have to ask ourselves is, how do I go from a 4 to a negative 20? I multiply by a negative 5. Negative 20 to 100, I also multiply by a negative 5. So now my next term, I multiply by negative 5 again. 100 times negative 5 is negative 500. And now I multiply by negative 5 again, which gives me positive 2,500. So if I look, I'm always multiplying by negative 5. So this is geometric. My common ratio, or the number I'm multiplying by each time, is negative 5. And now I want to find out my formula. So I'm going to do the exact same thing. I'm going to copy and paste that rule. So a sub n equals a sub 1 times r to the n minus 1. And in this case, my first term is a 4. And I'm multiplying by a negative 5 each time. So that's going to go inside my parentheses. And this is your final answer. A sub n equals 4 times negative 5 to the n minus 1. All right, let's look at this real-world connection. Miss Townsend plans to double the amount of time she spends walking per day each week. She starts on week 1 walking 5 minutes per day. After 2 weeks, she then walks 10 minutes per day. And after 3 weeks, she is walking 20 minutes per day, and so forth. Part A says write an explicit formula to represent Miss Townsend's plan to basically model her walk. time. So the first thing I'm going to do is I'm actually going to highlight some things. So week 1, we're at 5 minutes. 2 weeks, we're at 10 minutes. 3 weeks, we're at 20 minutes. So I'm going to rewrite those numbers. I'm going to write 5, 10, 20. When I go from a 5 to a 10, what do I multiply by? Times 2. When I go from a 10 to a 20, what do I multiply by? Times 2. So I can see that this is geometric, so I can write an explicit formula. And we know our explicit formula is a sub n equals a sub 1 times r to the n minus 1. And if you look, our a sub 1 is our first term, which is a 5. Now my common ratio is a 2, because that's what I'm multiplying by each time. So this is my final answer. A sub n equals 5 times 2 to the n minus 1. Part B says, if she keeps this up, how long will she walk on week 10? So that basically means I'm going to plug in 10 to my rule. So I get a sub 10 equals 5 times 2 to the 10 minus 1, because I'm just plugging in 10 to my rule. When I type that into my calculator, I get 2,560. So that means on week 10, she will be walking 2,560 minutes per day. So she'll be walking 2,560 minutes per day. Now, part C says, is your answer to part B realistic? Explain. Well, I have a question for you. Does it make sense that someone can walk 2,560 minutes per day? No, it doesn't. Because if you look at that 2,560, if I were to see what that means in one day, that means there are 42 hours in a day. Are there 42 hours in a day? No. So this is not realistic. And that's all you would need to write. And then you'd explain why, because there's not enough hours in the day. All right? So if you have any questions, please email myself or Miss Townsend. And today is just an EdPuzzle lesson. Tomorrow you're going to be doing a delta math on geometric sequences. Have a great day, ladies.